In this example, we are given that the figure shows a glass hemisphere M of refractive index 3/2 and radius 10 cm, and a point object O is placed at a distance 20 cm behind the flat face, which is viewed by an observer from the curved side. We are required to find the location of final image after two refractions as seen by this observer. Now in this situation, as the first refraction is by a flat surface where object is located at distance 20 cm from the flat surface. If this distance is considered as h, here we can write after first refraction, image is produced at a distance. We already studied in previous section that this distance can be directly written as mu h, which will be 3/2 multiplied by 20, that is 30 cm. That means the light rays which are incident on the flat surface from object are refracted in such a manner that these appear to be coming from a point which is behind the object at a distance of 30 cm from the flat surface, or we can say this is the position which can be considered as the first image I1. Now this image will act as an object for the spherical surface on which the light will incident, and we are given that the radius of curvature of this hemisphere is 10 cm. So we can write for second refraction at a spherical surface, we can use here the data we can use is u is equals to plus, this will be 30 plus 10, this will be plus 40 cm. Radius of curvature we can consider as plus 10 cm. Mu1, the refractive index for the incident ray medium is 3/2, and mu2, the refractive index of the medium in which the refracted ray will come out, will be 1. And using these values, if we use refraction formula as mu2 by v minus mu1 by u is equals to mu2 minus mu1 by r. On substituting the values, you can see here we'll be getting 1 by v minus mu1, 3/2 multiplied by 40 is equals to mu2 minus mu1. This 1 minus 3/2 upon r is 10 cm. Here if we simplify this relation, here we can see the value of 1 by v we are getting is this will be 3/80 minus, and this will be 1/20. On further simplifying this, we are getting the result to be minus 1/80. That means we are getting the value of v to be minus 80 cm, and that will be the answer to this problem. That means the observer will see the final image of this object at a distance 80 cm on the left side of this pole. That means the light rays will be converging and producing an image on the principal axis. If the observer is located far away, he'll see the final image to be located at a distance 80 cm from this pole, as the value we are getting is minus 80. But if the observer is quite close to the spherical surface, then you won't be able to see anything if its position is at a distance less than 80 cm, because converging rays will incident into the observer's eye.